This video is going to introduce you to the harmonics of open tube instruments. What is an open tube instrument? It's one that has the air free to move in and out both ends of the instrument, and the instrument itself is cylindrical in some way. Some examples of this are the organ tubes and a recorder, a pan flute, and a traditional flute. Some students comment that the traditional flute has the one end closed, so how can it be an open tube instrument? Well, that's true that it has the one end that is closed. You do have to keep in mind that right there is an open end where they're blowing the air in and out. So it is actually an open tube instrument. So let's actually draw the fundamental harmonic pattern for an open tube instrument. So we've said what defines an open tube is the fact that you have the two ends where air is free to move. If you have places where air is free to move, then that is going to have to be an antinode. So we're going to have a lot of movement of air in and out both ends. So the next question is this the harmonic pattern? No. To be a harmonic pattern, you need to have at least one antinode and one node within it. So we need to add actually a node right here in the middle. And how do we know it's going to be a node in the middle? Well, if you think about it, you're going to have air coming in and out of the left side. So in the middle here, you're going to have air pushing to the right. If you think about it, you're going to have air coming in and out of the right side. So in the middle here, you're going to have air pushing to the left, and the place where those forces are going to be equal is exactly halfway in the middle, and you will have both of these forces cancel out to be zero, and so there's going to be no air movement in the middle of our tube. So what you're seeing on the screen now is a simulation of the air particles inside of the tube. You can see that they have movement on the two ends and very little movement in the middle. You can also see that here with this displacement graph where we have the antinodes on the ends and node in the middle. You may ignore the bottom graph. And what we can find is that this tube has a length of 0.748 meters, and as a result, it has a frequency of 230 hertz. So if you look at what I have now on the screen, I have actually moved this up so it shows the second harmonic. Sometimes they call that the first overtone, so that's why you see that for vibrational mode. But this is the second harmonic. What you can see is that our standing wave pattern has gotten more complex. We have an antinode on the two ends still. But now what we have is we have node, antinode, node. In our standing wave pattern. You can see that the movement of the wave particles within the tube reflect that. We have movement at the end, a spot right here where there's very little movement, a lot of movement in the middle, no movement, a lot of movement at the end. And if we actually look at the frequency of this harmonic, the frequency of this harmonic is 459 hertz, which is very much approximately 2 times what we found for the first harmonic. We found our first harmonic was 230 hertz for this particular wave, and now that we found that, it's basically 2 times, almost exactly 2 times the frequency. So we have ourselves here a second harmonic. All right, let's look at a third harmonic. Let's go up one higher. You can see now that the third harmonic for our open tube is even more complex. We still maintain those antinodes that are on the end. But we now have added an additional antinode and node within our wave. And you can again see that with the displacement here that we're getting a lot of displacement here, none, displacement, none, displacement, none, displacement. And again, if we look at our frequency, we can see that this frequency is almost exactly 3 times the fundamental. They're not coming up exactly 3 times because our fundamental must have been not exactly 230 hertz. It must be some fractional frequency, but you can certainly get a sense that we are seeing that frequency double with the second harmonic and triple with the third harmonic. And let's just go up a couple more. Oh, that's as high as it goes. So take a minute and look at this on the screen. See if you can figure out what harmonic it is by the pattern of A's and N's. All right, if I look at this pattern of A's and N's that is on the screen, what I see is 1, 2, 3, 4, 5, 6 nodes. And that is going to be a sixth harmonic. If you haven't caught on to easily get the harmonic number for any open tube, you want to count the number of nodes. The N's give you the harmonic number within the pattern. We can double check that against the frequency. You see the frequency here is 1,378 hertz. If I divide that by the fundamental for this tube of 230, I do get a number that is very, very close to 6. So we have established that the first harmonic for an open tube has the pattern ANA. The question is, how much of a wave is in this tube? To answer that question, I actually want to think back to strings for a minute. What you'll see here drawn on the screen is not actually the first harmonic for a string, it's the second harmonic, but that's not what's important. What's important is that this picture of a standing wave on a string shows one full wave. We have a full crest, a full trough, so the full length of this is one wave. It is showing us indeed that we have one wavelength. And so if I look at this here, what I can see is if I look right here, that here I am going to have half of a wavelength. And if I look right here, I'm going to have 1/4 of a wavelength. That tells us something very important about standing wave harmonic patterns, that going from one N to one A is always going to be 1/4 of a wavelength. So if we are going to actually think about how much of a wave we have in this tube, we use L for the length of the tube, I can see that I have 1/4, 2/4, or 1/2 of a wavelength in my tube. Now, if I think about that even further, rearrange this equation for wavelength, what I'm going to see is to get one full wave, I have to multiply the length of my tube by 2. So my wavelength for this tube is going to be 2L over 1. If I expand that even further, what we will find for open tubes is that their wavelength for any open tube harmonic is going to be equal to 2 times the length of the tube over N, where N is the harmonic number. So to kind of compare both strings and open tubes, they both use the wavelength equation of 2L over N. But the open tube has antinodes on the ends and nodes in the middle. And to get your harmonic pattern for the open tube, you're just going to count the nodes. Another thing that is worth noting is that for all standing wave harmonics, no matter what it is, strings, open tubes, closed tubes, whatever, as you go up higher in your harmonic number, you are fitting more waves within the same length, which means your wavelength goes down as your frequency goes up. That's also kind of important to note.